So moving forward on light, now that you have a little bit of picture of what light's about based on that fun 10 ed video, let's take a look at light in other contexts. So we already talked about the fact that light is an electromagnetic wave, and the video went into the details that light is, this is what we mean by a wave, and that a wave has a wavelength like this, and a frequency. In other words, how often those bumps pass a particular point. So because light is an electromagnetic wave, that means that electrons are going to be affected by light passing through. You can actually see the pattern of the wave of the light as it passes through a field of electrons. Now, this might not blow your mind, but it blew a lot of scientists' minds when it first came out more than 100 years ago. And this is the idea that light is not just this kind of kind of a wave, it's also simultaneously a particle. So particles of light are called, if you remember, yes, photons. And each of these photons have properties of, just like, each of these photons has the properties of both a wave and a particle. So it can be characterized by wavelength, just like a wave. And it also has a characteristic frequency. And from that wavelength and frequency, we can come up with its energy. So the energy of a photon depends on its frequency. This is a really important concept. So we're just going to go ahead. I'm going to take my important concept color here. Once again, you don't have to use my important concept color. I'm going to use my orange highlighter to indicate that this is something that might pop up again. So important relationships. So this relationship right here this is lambda times F equals C. Here lambda equals wavelength, F equals frequency, and C equals the speed of light. So a simpler way to write this would just be wavelength times frequency for any speed of light is equal to, all light travels at the same speed. For any frequency and any wavelength, we'll give you the speed of light. Now, this is the same for all light. So it doesn't matter if it's a radio wave or if it's a gamma ray or if it's visible light, the speed of light is going to be the same. What's changing for each one of them is the wavelength and frequency. So for example, radio waves have a long wavelength and and are low frequency, whereas gamma rays have a very short wavelength and a really, really high frequency. But no matter what kind of light you're talking about, if you multiply that particular light's wavelength by its frequency, you'll always end up with the same speed of light. And that speed of light, C, this right here is our speed of light. Speed of light is equal to and we should say in a vacuum, or we could say in a vacuum because you can slow down light. Is equal to 300,000 kilometers per second. Okay. So, or we could say 300 million meters per second. So it's not just the speed of light. Speed of light is not just about light. Speed of light is deeper. It's the speed of causality. Nothing can go faster than the speed of light. Which I know would ruin a whole bunch of, that's an N, not an H. A whole bunch of science fiction movies cannot happen anymore because this is a rule, but this is a real rule. If this is untrue, all sorts of other kooky things would start to break down. And like, for example, you would end up with things being able to go back in time or having infinite mass. Now, similarly, you can, from the photons, from the frequency of the photon, times this is Planck's constant, you can then end up with the energy. Now, we're not going to use this equation quite so much, but just know that the frequency and the wavelength determine the light wave's energy. I should say, and wavelength determine light waves energy. Makes sense? So this discussion question is a little confusing. Which wave has the next most energy and why? What's going on here? The image is actually on this page over here. So taking a look at this image over here, right over here. So thinking of this relationship, this is a constant. So this number, this H right here never changes. So as the frequency goes up, the energy goes up. So here we have 3 different waves, and you have one that is a frequency of 30 gigahertz, one that has a frequency of 60 gigahertz, and hertz is, so going back to those units before, hertz is hertz, and it means per second. So that's 1 over S. It's per second. Okay, and it's a unit of frequency. Gigahertz, if you remember back to that first unit that we did together, not the introductory stuff, but the first meat and potato stuff that we did, giga means what? So that's right, it means a billion. So this is a billion hertz. In other words, when you say 30 gigahertz, you mean 30 billion times per second. So this is 30 gigahertz, this is 60 gigahertz, and this is 120 gigahertz. Which one do you think has the highest energy? Well, go back over the problem. Higher frequency, higher energy. So which one has the highest frequency? This one, right? So we would say which one has the most energy? The 120 gigahertz, because it is the highest frequency. So 120 gigahertz because it has the highest frequency. Now, on this last little bit over here of the electromagnetic spectrum by NASA, so this is a great diagram from NASA's website. This shows us the visible light, and it shows us parts of the atmosphere that are being absorbed by different wavelengths. And the atmosphere, actually, if you take one of my other classes, this is what protects us from the angry radiation from the sun. So the atmosphere is opaque to several types of waves in the atmosphere. Thankfully, not radio waves, so we can use them to send signals. You can't hear radio waves, really. Radio waves are used to carry a signal that we then turn back into sound. It is not itself sound. Similarly, it's opaque to quite a few other things, but it's visible to many types of visible light. So this wraps it up for part 2 of Workbook 3. Hang on to your butts because we're going to head on to the next part very shortly.